In this video, we will bring in everything we have discussed so far in this chapter. If we know the engine speed in revolutions per minute, the force acting on the gear, and the radius of the gear, we can calculate the horsepower of the gears. Here we have gear A spinning at 2,500 RPM with 10 pounds of force being applied. The radius of gear A is 6 inches. We also have that gear B has a radius of 3 inches. We want to know what the horsepower is for both gears. Remember, horsepower equals RPM times torque divided by 5,252. But in order to find the horsepower, we have to find the torque. First, we need to find the horsepower on gear A. The equation that we need to use is horsepower is equal to the RPM multiplied by torque divided by 5,252, since we are looking at rotational power. We can substitute in what we know. We have 2,500 RPM multiplied by the torque divided by 5,252. However, we don't know what the torque on gear A is, so we have to find this first. Remember, torque is equal to the force applied multiplied by the radius of the gear. So we have 10 pounds multiplied by 0.5 feet, which is 6 inches converted into feet. This gives us 5 foot-pounds of torque. Now we can substitute 5 foot-pounds of torque into our formula, and calculating, we see that the horsepower on gear A is 2.38 horsepower. Now that we have the horsepower of gear A, we want to find the horsepower on gear B, which is equal to the speed of gear B multiplied by the torque on gear B divided by 5,252. But since we don't have the speed of gear B, we need to find that before we can find the horsepower. Remember, the angular speed of two gears with different number of teeth will not be the same, so the speed of gear A is not the same as gear B. We can find the speed of gear B, which is our driven RPM, by taking the driver RPM multiplied by the ratio of the number of driver teeth divided by the number of driven teeth. So the driven speed, or the speed of B, is equal to 2,500 RPM multiplied by 40 teeth divided by 20 teeth. This gives us a speed for gear B of 5,000 RPM. Now that we have the speed of gear B, we can find the horsepower on gear B. The horsepower of B is equal to the speed of gear B multiplied by the torque on gear B divided by 5,252. In the previous slide, we found the speed of gear B to be 5,000 RPM. However, we don't have the torque on gear B, so we need to find that first. The torque again is equal to the force multiplied by the radius of the gear, so the torque on gear B is 10 pounds multiplied by 0.25 feet, which is the same as 3 inches. This means the torque on gear B is 2.5 foot-pounds. Therefore, to find the horsepower on gear B, we take 5,000 RPM multiplied by 2.5 foot-pounds and divided by 5,252. This means the horsepower on gear B is also 2.38 horsepower. What we have found in this example is that the horsepower is conserved, meaning it stays the same between gears in a gear train. Unfortunately, this only happens in a perfect world, not in reality. In reality, gears are only about 94% efficient, so the horsepower at B will be slightly lower than at A due to friction, among other things. This concludes our discussion of rotational power.